Alright, good day guys, how are you all doing? So when we talk about partial differentiation, it's much more like you having a normal differentiation we do talk about before is y with respect to x, right? And I want to break it down by using what we call a man marrying a single wife and a man having multiple wife. Multiple wife. So we know that the moment you have y equals to x, just a normal man having what a single wife at which it depends on as a particular variable, the y dx will be equals to 1. And at times we call y also as a function of the variable you are being given, which is function of the x. So f prime x, that's differentiating x just once also, you have this to be equals to 1. This is talking about a single variable. But partial differentiation now talks about a certain process whereby, let's assume you have y equals to x plus z. Let me even put additional, let's say plus let's just leave that one like that, s plus z. Now at this moment you should know that you are having two particular certain variable whereby y is a function of x and also a function of z. Then when you are being asked to differentiate this kind of proof test, what do you think you can do? Now this one is a single man having two particular wife, and you should know that when it comes to night and you want to spend some time with some of them, you might decide to say I want to take them one by one. Okay, today this is S turn, tomorrow this is what Z turn. So the moment you try to actually take a U-turn in that process, I could tell you that, alright, since tonight is S turn, I don't want to see anybody again except from S in my bed tonight. That means that any other variable or any other wives, they are treated constant. Are you with me? There's not one thing you need to understand about the dangerous or how dangerous the constant is. If I have when I said I treated this as a constant, that means that I'm talking about z not becoming a variable anymore. It is now either you saying 1, 2, 3, and whenever you differentiate a constant, what will it give you? 0. But the moment z, let's assume you have y equals to, now look at the difference I want to try to make with you guys. Let's say you have zx. Now this is two different things. Now if I differentiate this, I will explain why I use this sign or why I use this. Now if I said the y over the x, that means I'm telling you that differentiate y with a coefficient of x is normal way to differentiate. I differentiate x normally and that gives me what? 1. But the problem is that I will treat z like a constant, that is taking it as 1 or I take it as 2 or anything I want to take it as. And in that point, whenever I take it as that, I have 1 plus what? 0, and that gives me what? 1, right? But what I want to tell you is that you should know that if it was that I have something like y equals to 2x, if I'm to differentiate y equals to 2x, what am I going to have? 2. Don't forget. That means that at that particular point in space, 2 is a constant, right? But it does not turn 0 because it is attached to the variable. And we know how this works in normal L'Hopital's rule, in monomial differentiation. So the moment also you have y equals to what? Zx. And I tell you the y over the z. In that point, I'm taking z as a constant. That is, if I'm to differentiate x taking z as a constant, my answer will be giving me what? Z, times, this is just a power of 1. 1, you have 1 times x, the raised power 1 minus 1, don't forget the normal rule, and that will be giving me what? My z. Can you see what I'm saying? So can you see the difference between this? Because you have this as plus z stands alone as a constant. In that process, it turns to what? 0. But since it's attached to a variable here, we have to what? To multiply with that variable without not touching it at all. So I hope you understand some certain things under partial differentiation. Now, it's just a question whereby I differentiate a particular variable, taking the other one as a constant. Are you with me? And this usually helps when you are dealing with a lot of things like when you get to like Tokyo equations, and when you have equations that deals with two variables and you are asked to break some of them down, or you are trying to differentiate one with respect to the other one and keeping the rest constant. Are you get what I'm saying? So in this case now I'm differentiating what? X by keeping z constant. So how do we give a good definition of partial differentiation? We only have two certain orders, though. Two orders to deal with basically. That's the first order partial differentiation and the second order. And when you talk about the first order, it's just like a normal way of you having the y dx equals to normal the y dx, and you have second differential equation whereby you have the square y over the x squared. That's the same thing for partial differentiation also. whereby you have your first order to be the y, let's just say the y over the x, and the second order you have the square y over the x squared. So stuff like that. So let's go to something simple to explain to ourselves. So at this particular point in space, we have we say that what introduction to partial differentiation. It says that when differentiating a function having two or more variables, we differentiate one variable with what while keeping the rest of what of the variable constant. Are you with me? So under the first order partial differentiation, it is denoted with a column. You know, instead of whereby you have a change in y, which we call the y, for normal differentiation, we are going to be using what a column d for partial differentiation. Are you with me? So from there we say that what it denotes a differential coefficient. Are you with me? In an expression containing more than one variable. So if you look at now, let's assume I have v equals to pi r square h. So from my point now, let's assume I wanted to differentiate r. In that moment, me differentiating r, I've kept, though pi is constant already, is a constant variable, that means I've kept what h being constant. So that is, I will say what the v over the r. And at that point, differentiating this, literally I have my pi, right, times differentiating r normally. Since h is with r, you don't differentiate h to become 0. You just leave it alone like that normally. What we are differentiating is only going to be what the r square. At differentiating r square, you have what 2r then times your h. So in that point, the v over the r will be equals to what 2 pi r h. Are you getting what I'm saying now? So that is also a good explanation on how to break things down. So let's take this example one as a simple model to orchestrate partial differentiation. So the point here tells us that given the z is equals to 5s quatic plus 2x cubed y squared minus 3y, find the z over the x. So that point, you know, x is normally a normal variable here. This becomes what? Differentiating 5s to the power 4, you have this as 20 x raised to the power 3 plus. Now, like I told you that since you are differentiating x in this point, that means y will be kept constant. Nothing concerned with whatever you are doing. It's just like you saying y being constant. So you have this as 2 times, you get what I'm saying? Or you can just put them one side. You have 2y squared while we are differentiating what? Your s cube. And whenever you are differentiating s cube, you have what? 3s squared minus what? Now, whenever you are differentiating 3y, since y is kept constant, are you with me? Constant times constant. What will this 3 result to? Constantine. So it's just like me saying minus 3 times 3. Or me saying minus 3 times 2. That will give me what? Minus 6. If I want to differentiate minus 6, what am I still having? 0. So since you have constant together, even though y is just signifying one kind of present thing, you still have it what being equals to 0. If it was that you have x and y together, you know this one will become ordinary y, because this one is the variable we are talking about. But since y is a constant, you still have a constant again. Double problem, you get. So it has to repel. So in this point now, the z over dx, you have 20s cube plus 3 times 2, you have 6x squared y squared. So that is that for that one. Then the second one tells us that the z over the x over dy rather. So at that particular point, now that means you are differentiating the z function with respect to the y variable. So in that point, this will give us automatically 0. Don't forget. Plus, now, like I told you, 2s cubed will be kept one side. Then we differentiate y squared, which gives us what? 2y minus. You should know that since y is a variable here now, you can differentiate it normally, and that will give us minus 3. So from this, you have this being equals to 0 plus 2 times 2, you have 4s cubed y, then minus what? 3. And that will give you 4s cubed y minus 3. So this is like the KG1 aspect, you know, like a baby aspect of partial differentiation. Yeah, just to begin with.